All right, factors that affect position of equilibrium. So the question is, with chemistry, how can I help drive it forward so that I get rid of my reactants and produce my products? Or maybe I want to drive it backwards, right? I don't want some product showing up. So what can I do to drive it backwards? Well, I can change the concentration of either the reactants in the products to help shift it. Pressure can shift it in either direction depending on what the reaction is. Volume just goes with pressure, right? Changing the volume changes the pressure. Or I guess changing the volume could also change the concentration. And then there's temperature. Some reactions are driven forward by an increase in some temperature. Some are driven backwards by an increase in temperature. Catalyst. Adding a catalyst has no effect on the position of equilibrium. It just speeds the reaction up in the forward direction to get to a position of equilibrium, but it's not going to have an effect in terms of how much reactant I lose or product I make. The reverse rate of reaction is equal to the forward rate of reaction when I hit those concentrations, regardless of. Catalyst just lowers the activation energy to get to that position of equilibrium, so it has no effect. So let's go through. All right, Le Chatelier's principle. If an external stress is applied to a system at equilibrium, the system adjusts to try to relieve that stress. So, for example, I want to increase the yield of my product. What I could do is increase the concentration of the reactant, right? The system would respond to try to lower that concentration of the reactant, and that would help drive it forward. So let's say, for example, I want to get rid of a particular reactant, in comparison to another reactant, right? So adding up the one reactant will lower the concentration of the other and drive it forward. Well, I get a really low concentration of the other reactant. I could remove the product, right? If I remove the product, the system will respond to try to replace that product. So that's another way to drive the reaction forward. So if I have nitrogen reacting with hydrogen to make ammonia, if these are my equilibrium concentrations, putting a whole bunch of ammonia in here, well, the system's going to respond to try to lower that concentration. Concentration of the product is too high, so the system will shift backwards to lower that 3.65 molar concentration, raise the concentration of the reactants. Of course, I could solve for this by taking that 3.65 and those other concentrations, plugging them into Q, and comparing Q to K. I'll slide back a little bit. So K is 0.00237, and I have a Q value of 0.0286. Q is greater than K. That means you have too big a numerator. The system's got to respond to make that numerator smaller. Drive it backwards. All right, so for example, let's say I have barium sulfate in equilibrium with barium ion and sulfate ion, and I want to lower the concentration of the sulfate ion. Well, if I keep putting in barium ion, the system will respond to keep driving back towards the barium sulfate side and keep lowering the concentration of sulfate. So as the concentration of barium gets greater and greater, the concentration of the sulfate gets less and less in order to be equal to that equilibrium constant. Same with the barium ion concentrate. As I add a whole bunch of sulfate, the concentration of the barium would have to get smaller as I drive the reaction backwards towards the solid. Of course, adding solid has no does not change the position of equilibrium. Adding more solid just increases the forward rate of reaction at the same rate it increases the reverse rate of reaction. So solids don't affect the position of equilibrium. All right, changes in volume and pressure have little effect on solutions, but can have a big effect on gases. And the way it works is if you increase the pressure on a system, the system will respond to drive to the side with less moles of gas. So when I look at the coefficients in this reaction, 5 moles of oxygen gas on the one side, 2 moles of sulfur tetroxide gas on the other side. If I increase the pressure on this system, it's going to drive to the side with less moles of gas. It's almost like the system wants to lower the pressure, right? You've increased the pressure, so the system will try to lessen the pressure by driving to the side with less moles. So this could be a way of driving this reaction forward. Put it under pressure. That'd help drive it forward to make more lead oxide and sulfur tetroxide. Phosphorus tetrachloride in equilibrium with phosphorus trichloride and chlorine. I have 1 mole of gas on the reactant side, 2 moles of gas on the product side. So if I increase the pressure on this system, it'll drive to the side with less moles of gas. It'll drive backwards. So this could be a way of stopping this reaction from happening, right? Increase the pressure and it'll keep it from going forward. It'll drive it back towards the reactant side. With this system, I've got 2 moles of gaseous reactants, 2 moles of gaseous products. So in this situation, putting pressure on this will not shift it to either side. This will not be a way of shifting the position of equilibrium. So it only works when you have an imbalance, more moles of gas on one side of the equation than the other. All right, changes in temperature. Equilibrium constants are temperature dependent. So if you change the equilibrium, if you change the temperature, you change the value of K. So a temperature increase favors an endothermic reaction, and a temperature decrease favors an exothermic reaction. So you can almost look at it like heat is a reactant here. If I increase the temperature of the system will respond to drive to the side where there's no kilojoules, right? So it'll drive to the product side. So an increase in temperature will drive this forward, right? I had to put heat in to make this happen, so increasing the temperature will help drive it forward. All right, so here we have cobalt hexahydrate complex reacting with chloride to make cobalt chloride complex and water. So as you can see, and maybe you can't, well, yeah, you can. You can see it on your full screen there. This is an endothermic reaction, all right? So endothermic reactions are driven forward by heat, all right? So if I increase the temperature on this, I drive it to the blue complex side, right? So you see the water cobalt complex is pink, the cobalt chloride complex is blue. So increasing the temperature in this will drive it forward and make it more blue. If I put it in ice, that'll drive it backwards, all right? So it'll drive it back towards the pink. So we'll have to do this demo in class, right? Heating it drives it forward, cooling it drives it backward. It's endothermic reaction. All right, so as we said, the effect of a catalyst. The catalyst has no effect on the position of equilibrium. It increases the forward rate of reaction the same rate as it increases the reverse rate of reaction. So you're just lowering the activation energy in the forward direction by adding chlorine radical. But you're also lowering the activation energy in the reverse direction. So you're going faster in both directions, faster forward and faster backward. All right, the Haber process is kind of a famous process. In World War I, it was essential to make ammonia for making gunpowder, right? So the Haber process, you're reacting nitrogen and hydrogen to make ammonia. As we can see, heat is released during this, so it's an exothermic process. And it's a pressure reducing process. So the way to increase your concentration of ammonia is to put this under pressure. So if I put this under high pressure, that'll drive the reaction forward, and you'll maximize your reaction between hydrogen and nitrogen to produce ammonia. All right. 4 moles of gaseous reactants, 2 moles of gaseous products. Increasing the pressure drives it forward. It's an exothermic reaction, so doing it at low temperatures would drive it forward. Now, the problem with that is it makes it very slow. So there's a happy medium here. Carrying out at low temperatures will drive it forward. But in the end, you end up doing this particular process at about 500 degrees Celsius. Not too hot to decrease your yield that much, but at the same time speeding it up enough to get to a product. So all reactions go faster at high temperatures, but some of them don't go as much to completion. So exothermic reactions, less spontaneous at high temperatures.